We know from previous chapters that the population is the entire group in which we're interested in gathering information about. Most of the time, it's not possible to conduct a census and gather data from all the individuals in the population, so instead we take a sample. A sample is a subset of the population. A survey of 1,353 American households found that 18% of the households own a computer. The population is all of the American households, but since it's not practical to get information from every American household, we take a sample of 1,353 American households instead. The average weight of every sixth person entering the mall within a 3-hour period was 146 pounds. So the population could be defined as people in general, or we can narrow the field to the customers at the mall. And of the customers at the mall, we sampled every sixth person within a 3-hour period. As we begin to use sample data to draw conclusions about a wider population, we must be clear about whether a number describes a sample or a population. A parameter is a number that describes some characteristic of the population. In statistical practice, the value of the parameter is usually not known because we cannot examine the entire population. An easy way to remember is that P goes with population, therefore P goes with parameter. A parameter is something that comes from the population. A statistic is a number that describes some characteristic of a sample. The value of a statistic can be computed directly from the sample data. We often use a statistic to estimate an unknown parameter. S for sample, S from statistic. A statistic comes from a sample, whereas a parameter comes from the population. A survey is conducted of all 128 of Ms. Hammond's students to find out the proportion who are left-handed. She was surprised to find out that of all the students, 18% are left-handed. One of her statistics students took a random sample of 45 students and finds that 25% of those surveyed are left-handed. The population are Ms. Hammond's students, all 128 of them. The statistics student took a sample of 45 students, randomly. The parameter of interest is something about the population that we're interested in studying, and that is the proportion of students who are left-handed. In this example, 128 represents the population size, and the notation we use that is capital N represents the population size, in this case being 128. 45 is the sample size. We know that the variable that represents the sample size is lowercase n. 18% is the population parameter. Since this is a proportion, we use the letter P to denote the proportion, 0.18. 25% came from the sample, that is a statistic. The symbol that we use for a proportion that comes from a statistic is called p hat. Our next example, of all 150 employees who work at Target and Burke during the month of December, the average number of hours worked per week is 42.7 hours. A random sample of 20 employees was selected, and of them, they worked an average of 45.9 hours. The population are all the employees who work at Target and Burke, so 150. The sample is a random selection of 20 employees. What we're interested in knowing about the population is the average number of hours worked per week. In this case, 150 is the population size, which is capital N. 20 is our sample size, which is lowercase n. 42.7 is our population mean. It comes from population. We use mu to denote the population mean. 45.9 comes from our sample, that is the sample mean. The notation for that we already know is x bar. So all of our symbols look like this: population size, capital N, sample size, lowercase n. Population proportion is a percentage or decimal, is lowercase p. A sample proportion we call p hat. When we're talking about the population mean, we know that as mu, sample mean is x bar, and our population standard deviation we know is sigma. Here we have s. Please take a moment, stop the video, and see if you can write the appropriate symbol that goes with the numbers provided. It's not surprising that two different samples generate different results because they may not contain the same individuals. This is called sampling variability, when the value of a statistic varies in repeated random sampling. When sampling, our goal is to use the statistics to draw conclusions about the population, so we want our sample statistics to be as accurate and reliable as possible. So imagine the bullseye below on your paper represents the population parameter, and the arrows fired at the target as the sample statistics. Our goal is to get as close to the population parameter as possible, so as close to the bullseye as possible, while also being reliable and consistent. So both bias and variability describe what happens when we take many shots at the target. Bias means that our aim is off and we consistently miss the bullseye in the same direction, or our sample statistic is an over or underestimate of the parameter. Variability means that repeated shots are widely scattered on the target. The sample statistics vary widely from one sample to another. So looking at target A, we see that the majority of the arrows have been shot in the same direction away from the bullseye. However, all of the dots are consistently close together. So the bias is high because it is not close to the middle, and variability is low because the shots are close together. In our next target, we see that the shots are all around the bullseye, so they aren't all an overestimate and they're not all an underestimate. So we would say that the bias is low. However, the shots are pretty spread out. They're not close together, so they're not consistent. This would be high variability. Again, here we have high bias because the majority of the arrows are away from the target in the same direction, not all over the place. And the variability is high also because the dots are all scattered. Letter D is the example of something that we want to happen. Notice that these are all low bias because they are equally around the bullseye, and it's low variability because they are all consistently close together. When taking a sample, we want D to happen. We want our bias to be low, we want all of our sample statistics to be centered around the actual value, and we want the variability to be low. We don't want statistics that are all over the place. So to decrease bias, we already know how to decrease bias. That is by taking a random sample. To decrease variability, we want to increase the sample size.